This is our second video of sample problems on equivalence relations and the third video overall on the topic of equivalence relations. We should now be ready for a more advanced sample problem. Please refer to your note pack if you'd like to have space to write about this problem. So this time our set X is going to be just 5 integers, 1, 2, 3, 4, 5, and we are going to define R on the power set of X. So there's a lot of things that we need to recap real quickly before we start the problem. Remember, the power set of X is the set of all subsets of X. We also need to remember that the power set of X is going to have 2 to the size of X elements in it. So since there are 5 elements in X, we are going to have 2, 4, 8, 16, 32 elements in the power set of X. So we are defining this relation on 32 elements, and those 32 elements are the subsets of X. So an example of one of those elements would be the empty set. An example of another of those elements would be the subset 1, 4. An example of another one would be 2, 3, 4, 5. So there are 32 of them, and we are going to define a relation on them that A relates to B if when I take the subset and union it with 3, it's the same as if I take the set B and union it with 3. Okay, so we're going to take some really small steps to sort of understanding this more complicated equivalence relation. So first we're just going to ask if two things are related to each other. Does 1, 2 relate to 1, 2, 4? So what we're asking is, does 1, 2 union 3 equal 1, 2, 4 union 3? And the answer here is no, because the union over here is 1, 2, 3. And the union on the right is 1, 2, 3, 4. So no, 1, 2 does not relate to 1, 2, 4. And that means in this relation, there will not be any arrows going between the subset 1, 2 and the subset 1, 2, 4. Next question, does 1, 2 relate to 1, 2, 3? So now, again, we're asking, does 1, 2 union 3 equal 1, 2, 3 union 3? And in this case, they are equal because the left-hand side is 1, 2, 3 and the right-hand side is 1, 2, 3. And so in our digraph of this relation, we already know now that the subset 1, 2 is related to the subset 1, 2, 3. And actually, if I think about it, if A union 3 equals B union 3, then B union 3 equals A union 3, and so I have my symmetry condition too. So 1, 2, 3 is also going to relate to 1, 2. And if I think about it for another minute, I can probably convince myself that A union 3 equals A union 3 no matter what A is. And as such, I should be able to convince myself that this relation is reflexive. Moving on to our next question, we want to know, is R an equivalence relation? Is it reflexive, symmetric, and transitive? So I just argued to you that yes, R is reflexive, but let me just write out again the justification. My justification is that A union 3 equals A union 3 for all A in the power set of X. Symmetric, we already got an inkling of why this is symmetric on the previous page because we saw that 1, 2 was related to 1, 2, 3 and 1, 2, 3 was related to 1, 2. What we need to say here is that if A union 3 equals B union 3, then B union 3 equals A union 3. Lastly, transitivity. If A union 3 equals B union 3 and B union 3 equals C union 3, then A union 3 equals C union 3. So I have all three properties satisfied, reflexive, symmetric, and transitive, and so it is an equivalence relation. Now's where we really get into the meat of the problem in part D. What is the equivalence class containing the subset 2, 3? Meaning, what is the equivalence class whose representative is 2, 3? Or, in other words, what are all of the elements in the power set of X that are related to 2, 3? Okay, well, first of all, the thing we always know is that every element is in its own equivalence class. So I do know that in this equivalence class 2, 3, I am going to find certainly 2, 3 itself. Now, I would like you to pause the video and think about what else is going to be related to 2, 3. Okay, did you pause and try and figure it out? If you didn't, I'm going to give you a second chance now, and I'm going to tell you what you should do that would be excellent practice would be to list all of the elements of power set of X. 32 seems like a lot. It's actually not that many. It'll only take you a minute to write it down, and then ask yourselves, which of those elements of the power set of X are going to be related to 2, 3? So try that now. Okay, I'm going to give you another chance. I'm going to tell you that there should be 2 elements in this equivalence class. So find what that other one is. Okay, I hope you figured it out. The only other element in this equivalence class is going to be the subset that contains just the 2. Because those are the only 2 things that I can union with 3 to get 2, 3. And now before I move on, I'm actually going to give myself another question. I'm going to ask myself, what is the equivalence class containing the subset 1, 4, 5 as a representative? What does that equivalence class look at? Again, pause the video, think about it, try and come up with the answer. It definitely contains itself, and it has to be equal to whatever I union with 3. So 1, 3, 4, 5 is also going to be in this equivalence class, and nothing else, because if I took out any element of 1, 4, 5, then it wouldn't be there when I union it with 3, and I need it to be. And if I added anything else, likewise. So I see that this equivalence class also has 2 elements. All right, how many distinct equivalence classes are there? Meaning, if I looked at the digraph, how many distinct little clumps of connected vertices would I have? And what I need to do here, and the reason I did that example in part D, was you really need to convince yourself that there are exactly 2 elements in every equivalence class for this relation. In general, it is absolutely not true that all of the equivalence classes have the same size, but in this equivalence relation, every equivalence class is the same size. They each have size 2. So, in order to have 32 elements divided into equivalence classes of size 2, there will be 16 different classes. And I'll just give you some examples now. I'd have the set containing 1 and the set containing 1, 3. Those would be an equivalence class. Another way to think about it is, of course, to think about the digraph. And on the digraph, for example, the empty set and the set that contains just 3 are going to be related to each other in the digraph. And I can sort of also think about the big subsets So the subset containing 1, 2, 3, 4, and 5 is going to be related to the subset containing 1, 2, 4, and 5. And I hope you can convince yourself that there are 2 elements in each equivalence class and 16 different classes. Moving on to the last example for our videos today, we're going to let the set X be 1, 2, 3, and we're going to define another relation on the power set. So if you thought you were going to get away from power sets, you were wrong. And I'll give you another heads up, they're in the homework too. We're defining this relation on the power set of X so that AB, the ordered pair containing A and B, is in the relation. If A intersect B equals 1, we need to decide if R is an equivalence relation and either prove it or disprove it. So go ahead and pause the video and think for a moment about whether or not this is or isn't an equivalence relation. Okay, I hope that you have decided that it is not, and I'm going to give you a super quick proof why not. So I'm just going to look at the set 1, 2, and I'm going to intersect it with the set 1, 2. Their intersection is 1, 2. And that intersection is not just the set containing 1. And so that means that the set containing 1, 2 is not related to itself, so this relation is not reflexive. And boom, I am already well assured that this is not an equivalence relation, because it has to be all 3, reflexive, symmetric, and transitive. Just for fun, because I know this is fun for everyone, I would really like you to just take a shot at drawing the digraph of this relation, which is not an equivalence relation, and see what it looks like. So pause the video and do that. Okay, first I have drawn all of the elements of the power set of X so that I can think about drawing arrows. If you didn't get this far, please copy this down, pause the video again, and now try and put in the arrows where they belong. Alright, so those are all the edges. And now that I've drawn the digraph, I can see a few things. For example, I can see that this graph is symmetric, but unfortunately, this graph is not transitive. Let's talk about why not. So we have an edge going from 1, 2 to 1, 3, and from 1, 3 to 1, 2. So in order to be transitive, I would have to have a loop on the element 1, 2. But I don't, because as I pointed out here, 1, 2 intersected with itself is not 1. So in this case, in terms of reflexivity, being symmetric and being transitive, the only one we have is symmetry. I hope these power set examples really help you on the homework problems on equivalence relations, and please remember that you can ask me questions over email.